Thank you, and sorry I cannot be there in person this year. I've listened in on some of the talks this morning, and it sounds like a fun time. So today, I'm a theorist. My job, I've given myself the job today of trying to get you excited about some of the science that can be done with these low-frequency telescopes that are being built. And so I'm going to just sort of run through that and some of the stuff we hope to learn. Okay, so this is a timeline history of the universe with the Big Bang at the left and the present day at the right. And one of the goals of astronomy or cosmology and extragalactic astrophysics is to understand how we get from the very simple universe after the Big Bang to the complex structures we see around us today. And we've uncovered a lot of that story in the past 60 years or so. So for example, from the cosmic microwave background, we know that about 400,000 years after the Big Bang, when the universe went from being highly ionized to full of neutral hydrogen gas, it was very simple and there weren't any structures around. And then on the other end, we've used telescopes culminating at this point with James Webb to look farther and farther back in time at how galaxies have been growing. And at this point, we've seen galaxies as they were a few 100 million years after the Big Bang, and been able to trace their growth over time to today. But in between those 2 points, from 400,000 years after the Big Bang to a few 100 million years later, we have essentially no observations. And that era is particularly interesting because it's something called the cosmic dawn, when the first stars and black holes and galaxies grew in the universe. Now, as I said, JWST has been pushing hard to try to get into that era and has gotten us farther than anything before, but it's left us with a long list of big unanswered questions. I would say we now know that we understand less today than we thought we did before JWST launched. Some of those questions include, why do galaxies grow much faster than we thought? They're bigger and more luminous than we thought we would find. Why do black holes grow much faster than we had expected? They are orders of magnitude larger, it appears. During the cosmic dawn, a process is going on called reionization, when, remember, after the cosmic microwave background, the universe became neutral. Well, it remained neutral until photons from stars and black holes could spread out from their original galaxies and make little ionized bubbles in the universe. And as those bubbles grow and fill the universe, we call that reionization. And we think that happened around 1 billion years after the Big Bang, but we're seeing it unfold with JWST. And then finally, the question that we'll be focusing on today is, when did the very first stars start forming and sort of transition into the normal galaxies that we're able to see with JWST? These stars are called population 3 stars for reasons that aren't really that important, but they're kind of the first generation of stars, and they probably formed in very different ways from the stars we can see in the Milky Way. So it turns out that to reach and to answer especially the last question here, we need to go beyond JWST, and I'll show you why in a moment. And this is where low-frequency telescopes on the moon come in. So all of that neutral hydrogen that was around for the first billion years of the universe's history has a particular transition called the hyperfine transition. And this is where the spin of the electron can flip relative to the spin of the proton. And that corresponds to a very small energy difference that creates a photon with a wavelength of 21 centimeters, right? But that photon then must travel through the expanding universe for 13 point something billion years all the way to us. And its wavelength gets stretched out, so it ends up having wavelengths of around meters, okay, which corresponds to quite low radio frequencies. So 50 to 200 megahertz is sort of what we're talking about in this era, kind of like FM radios, okay? And it turns out there are big advantages to observing that from the moon. All right, so what I'm going to show now is what this 21 centimeter signal looks like through the cosmic dawn. Okay, so focus on the left panel here. This is a computer simulation of a slice of the universe as you would see it in this 21 centimeter line, okay? And not much is going to happen at first, but pretty soon you're going to see these blue spots start to appear. All right, that is when the very first stars in the history of the universe appear, and they flood the universe with light, and that light kind of switches on this 21 centimeter signal. All right, so that's happening now. Shortly after those stars die, they form black holes. Gas accreting onto the black holes produces X-rays, which heats the universe, and that turns the signal from blue to orange. Right, and then this last phase that just happened, all the black blotches appearing, that's this reionization process. Right, as these ionized bubbles grow, you're destroying the neutral hydrogen, so there can't be any more of this signal left. Right, so what we would like to do with this background is trace the history of this signal. So this is the same thing shown in a much simpler way. All right. So now instead of showing a map of the universe, this diagram is showing the overall average intensity of this signal as a function of time, where time goes from left to right. Okay, so at the left of the diagram, this is before those first stars have turned on, right? So it turns out the universe is invisible in this line. Once they turn on, right, they flood the universe, and that's when you get this downturn, right? That's the signature of the first stars. And look at the black line here, right? And then the black line turns back up. That's when the first black holes start accreting gas and heating the universe. Right? And then finally, at the far right of the diagram, the reionization process kicks in, destroys all your neutral hydrogen, and the signal goes away. Okay. So the exciting thing here is that this shape is determined entirely by how stars and galaxies and black holes are forming at early times. Right. So the black is kind of a best guess at how this is unfolding. The purple is if you take away this first generation of stars, right? It dramatically affects both the timing and the properties of the signal. I should say these calculations are by Sahil Hegde, who's a graduate student at UCLA. Okay, I want to call your attention to a couple more things here. The top shows the frequency corresponding to when these features are happening. All right, so as I said, we're at low radio frequencies, tens of megahertz for the bulk of this action. Right, that's why we want to build these telescopes, and it turns out it's hard to do on Earth. All right, and then this vertical line shows the most distant galaxy that has so far been detected by JWST. Okay, it's at a redshift of 14, which is better than we've ever done before. But at least according to this model, it's actually after most of the interesting action has taken place. Okay, so we want to go even farther than JWST can if we really want to observe this signal. Okay, so what would we learn if we could do it? Right, well, the timing and intensity and all this is determined by how fast the stars are forming in this very, very early history of the universe. Okay, and so now this plot is not showing the signal anymore. It's just showing the star formation rate through the universe. Again, time is going from left to right. Okay, at the right side of the diagram, the overall star formation rate, okay, the top blue line is relatively well constrained because that's where JWST can see. Right, but before that, we basically have no idea how these first stars are formed. So the different orange curves are different models for their formation. And you can see there's about a 2 order of magnitude uncertainty in how they are forming. And so if we can observe this, we can get at this completely unknown exotic population of stars. That's sort of a conventional astrophysics thing to learn. But it turns out that there are all kinds of more exotic things that affect how these first stars form as well. So this is showing an example about dark matter. Okay, so dark matter we think makes up about 80% of the matter in the universe, but we don't know really anything about its properties. And there are a lot of modern dark matter theories that actually say that dark matter can have some kind of other properties than just the gravity where it was invented to solve. Okay, and this is looking at a particular class of those theories called warm dark matter, where the dark matter is actually moving around. When it does that, it prevents clumps from forming, and so prevents the first stars from forming. And so in this diagram, where, time goes from right to left here, right, the different curves are different assumptions about this warm dark matter, and the y-axis is showing the star formation rate. Okay, so it also dramatically affects the star formation rate, so we can learn about this kind of weird cosmology things by looking at these first stars as well. All right, so I think I'm out of time, so I'll stop there, but I hope I've made you excited for the kind of science we can do at these low radio frequencies, and now you'll hear some about the instruments that people are working on.